we have simple workflow here. So this is a PCB emission workflow. I will first talk about how you set up the PCB model. Then we will talk about doing a PCB layout, PCB level simulation, extracting XYZ parameters, and then we will link it to a two-way coupling with our transient circuit model that includes a four-phase switching power supplies, and then we will extract the conducting emissions from circuit, and then we will couple that to our field solver, and then we will compute the radiated emission, and then include the PCB enclosure. So in this case, we are just adding some shieldings, but if you have like other victims, like for example, adjacent PCB that you are concerned about, you can use this PCB as a noise source and then put an adjacent PCB for more two PCB analysis, and then we'll compute the radiated emission there. Okay. Yep. So first, I will talk about the PCB simulation. So the PCB file that we can accept are the following. So Ansys EDB file. If you are using Altium designers for PCB layout, there's an extension there allows you to export a Ansys EDB file that you can directly import it to our tool here. It will include all the layer Stackup information, material properties, and basically what you design in the tool, it will be imported here. Or if you're using other tool like Cadence or any other design tool, you can choose to import like ODB++, IPC 2581. These two are the most standard ones, and we can also import BRD file. Okay, so once you import the PCB layout here, there's also a workflow wizard. So this workflow wizard simply help you verify your Stackup after you import your geometry. So the first step, verify Stackup. Here you will see the layer information, layer thickness, and material properties, and all of that. So you can, in case you want to make any changes to the material properties, all of that, you can make the changes here. So the board we are simulating here is a simple 4-layer board, and then it is if we look at here, it's a buck converter board. So we are stepping down from 12 volt, going through the MOSFET filters, and then we are stepping it down to 1 volt. Okay, so next is verifying pad stack. Here allows you to verify the vias if you have any. So you can pick and choose your vias properties, and then you can modify it here. The next one is verify the circuit elements. So along with your PCB, you will import all the capacitor, inductors, and resistor if there are any. So here you can go ahead and import those. So next one is verify the ground and power nets. Here is help you define the it can do auto identify, so you will bring in all the power and ground nets in here. So the next one is sanitize layout for simulation. What this does is basically sanitizing the power or the ground plane, make sure the geometry is clean, and then it's good for simulation. So we don't over mesh our PCB board due to unnecessary like small defects or small cutout type of things. So the sanitized layout can help you speed up the simulation. So next one here, assign as parameter model for capacitors. This one in Ansys library, we have a massive amount of capacitors from different vendors and different manufacturers. So in here, you can, for example, for this one, you can select the capacitor, and then you can assign, and then you can pick and choose the manufacturer, the series, the part number, and the values. Right, so we have common manufacturer like Johansson, Murata, Samsung, etc., TTK, and this is a massive library, and it includes all the real material property like ESL, ESR, and loss factor, etc. So if you you will go ahead and map your capacitor in this case. usually we do an auto match by value, and then you will automatically match your capacitor by value. But if you have a desired manufacturer you want to pick, you can go ahead and select that. The next one is you can assign spice netlist. So what this one does is, in case you have like a common mode choke, like a 4-port inductors, you can import the spice model for your 4-port inductors. So in this case, we don't have any, but if you have that, you can go ahead and assign it here. The next one, so coming down here, these are more simulation. So we can configure DCIR analysis, all of that. But in this topic, we are mainly going to talk about EMI, EMC. So the first item I would love to talk about is susceptibility analysis. So to run susceptibility analysis or compare SYZ analysis, the first step is create ports on your PCB. In this case, we are going to create ports crossing like the power supplies, all these capacitor inductor, the MOSFETs, and also at the end the controller. Okay, so to quickly configure ports, there are multiple ways to do it. One is we can use a generate circuit elements on components. What this one does is basically you can go ahead and select your device. For example, I select controller. My design is U1, and then I can select the positive terminal and then the negative terminal on the other side to create port. And then you simply just create port, and you will create the ports on the right-hand side here. Or another method is generate port on selected nets. So you can go to your left-hand side, single-ended nets here. You can select the net. For example, I select this net. Is it highlighted somewhere? So it's highlighted here. It's a small net. Let me select one that's more obvious. For example, I select this net, and then I can go ahead and select generate port on selected net, and then I can just check or cross out the device that I want to set up the ports. And then you will set your reference impedance here and the reference net. So usually for signal integrity, we usually use a 50 ohm impedance, but for like power plants and power ground plan and all of that, we use a lower impedance. In this case, we use like 0.1 ohms, and then you can click generate to generate the ports. So once you set up the ports, you go to home, circuit elements, and you will be able to see all the ports that you set up. Because this is a power board, so you can see all the reference impedance for this power board is set to 0.1 ohm. And then here you can see the positive terminal and the negative terminal nets. So once we set up the ports, we can just click OK. Now we can go ahead and run the simulation. For susceptibility analysis, we will do the compute induced voltage analysis. So what this does is simply apply an incident wave that hits your port, and then you will calculate the induced current and induced voltage on the port that you set up. So to define the incident wave, here we can define the frequency range for our incident wave. In this case, it's doing 5 megahertz to 5 gigahertz. I will leave that as default. And then you can do a single incident wave, like for example, a spherical incident wave or Cartesian incident wave. On the bottom left corner of the board, you can see we have this. We have an arrow. We have coordinate system for our incident wave. K means the propagating direction, and then E naught means the magnitude of the normalized magnitude of our polarization. So here you can see the incident wave is in negative S direction, and the polarization is in -1, which is into the page, in this case on Z axis. And you can also define multiple incident waves, and here is a spherical incident wave, and you can, for example, you can define multiple steps. If I do like a phi equal to 0, 0, 0, and then I do a theta. If I do stop from 0, stop at 90, and then I can do like a step size. For example, I do a 45 degrees per step, then I would get 0, 45, and 90. So you can see there are 3 vectors and 3 polarization. So in this case, the magnitude of the normalized polarization is normalized to 1 volt per meter. So once you have this set up, you can go to other options here. Here will help you configure the accuracy, and you can set a temperature. So there's a temperature dependent material for the capacity for some manufacturer of the capacitors, and dependent material for the material properties of the board. So here you can define the design temperatures, and then under multi-processing, here you can define the number of cores to use. The more cores you use, the faster it solves. So in this case, we are using 4 cores for this simple board. 4 cores is good enough, and it typically solve in couple minutes. So I already have 1 board that is solved. I'm just going to bring that one. So we don't just waiting for it to solve. So here you can go ahead and plot induced voltage, right? Here we can create ports, and then I already have all the results created. I will go ahead and show you the induced voltage. So here, this is kind of the induced voltage at the port. So from here, you can add marker, see at which frequency and which net. So in this case, when we highlight it, we should be able to see which net it is. This one is a U1 ground net, right? So it's one of the largest ground plane on the board. So it has more induced voltage and induced current. And in this case, it's inducing at around 1 gigahertz, and the other peak is around 2 gigahertz. Okay, so after that, this is the susceptibility analysis. Then we will go to compute SYZ parameters. The reason why we want to do this is because we want to couple our PCB field result with our circuit simulation. So I will do a transient analysis. In circuit, I will do a transient analysis. So in the frequency domain, I will include a DC points. So I do a DC points, and then I also sweep it up to 1 gigahertz. And when I launch, I will run the analysis, and then I will get SYZ parameters. Then we go back to our circuits here. So we go back to our circuit here. This is already a circuit that is set up. In this circuit, we have all these page ports. Here is where we will drop our SIwave, our PCB model here. So we will go ahead and select, and we will click SIwave, and then here we will bring in SYZ parameters. So if I do the demo, and if I open this one, and you can see the solutions is the SYZ sweep that you just did. And then if you click OK, this will create 27 ports. That's the number of ports we set up. But in this case, we have more than that. So we want to expose the reference pin to all these ports. So I right click, and then I can add individual reference pin per port. And then I will have a total, I have a lot more ports here, which includes the reference pins. So after this, I can place it in the right location. And then on the left-hand side here, on the top, you can see we have a voltage supply. This is a very similar setup in the lab measurement. We hook up our voltage supply to a lithium. In this case, we are using a 6x16 lithium. You can right-click and then component help. Here you can look at. You can see we have different module of lithium, or 6x15, 6x16, and 6x25. And here you will see the internal circuit for this lithium. And then from this lithium, we will connect it to our board, and then we have like 4 phase switches for this power supply. And all of these are connected to the board. And here we will also have the conductor and the inductor and capacitors here. The reason why we want to include it here instead of leave it in the board, because if you want to do parametric or optimization analysis, you can go ahead and do that. So if you can see, we set up the parameters for the inductors, and then you can basically set up parametric analysis or optimization analysis for it. So after that, we will set up our transient analysis. In this case, we just do a step analysis do a step transient of 0.1 nanosecond, and then we do it up to 200 microsecond. And then once we run the simulation, we are able to plot the results. So in this case, let's look at it. So here, this is the we are plotting the V out because this is not like a ideal design. So we can see it's not really stepping down to 1 volt. It's only at 0.6 volt. So this is the voltage at output, and we can also include the voltage at input here. So and then here we can go ahead and plot the conducting emission report. So this report, you can look at the conducting emission report, and then you can add like a standard mask. So in this case, we are adding like a FCC we're adding a FCC standard mask here, or 6x16 standard mask, and then you can check if your conducting emission meeting the requirement or not. After all of this, we can go ahead and right click on the model, and then we can do a push excitation. And what this does is pushing this transient result doing a FFT, coupling this result back to our frequency domain solver in the layout tool. So once we have that, once we couple the result, it will create a temp file that basically have the result from circuit, and then we will go ahead and compute near field analysis. So on the compute near field analysis, this setup is a setup from 10 megahertz to 1 gigahertz with 100 point linear steps. And then you can see this source file. This is basically the TMP file created from the circuit. And then you can configure the sweep for EMI analysis. What this one does is, if you only care about the saturation region of your circuit behavior, you can go ahead and set it here that only compute the saturation region. If you don't set it here, it will compute from time 0 to time 200 microsecond. And then on the bottom here, we will create like an offset value. What this does is simply create a Huygens box around your PCB board, and then we are specifying 3 millimeter at the board, right? 3 millimeter in all direction of the board, and we want to compute our near field results. And then once you have all of this, you can hit launch, and then it will give you a near field results. Right. So now we can plot the near field. I'm going to plot it at 10 megahertz. In this case, I'm plotting the E field. You can see I have a maximum E field plot here. I can plot the near field on our PCB here, and then you can look at just top, bottom, or the side. So you can basically just plot the field at different location, and this field is located at 3 millimeter away from the board. So the next step is you can also compute a far field. So you go to the top, compute far field. I'm going to hide the color plot for now. And then I can go to the simulation. I can compute far field. From here, I can create like a far field simulation, again, from 10 megahertz to 1 gigahertz. And then I click launch. I can plot out my maximum RE total for the far field results. And if we go back to our result here, okay, so SIwave far field result. Here we have our maximum RE total. This is by default is at 1 meter. If you are interested in to do a 3 meter far field report, you can do like a divided by 3. That is 3 at 3 meter unit is dB volt per meter. We will plus 120 to define it as dB microvolt per meter. And then once we apply, we can see that now we can see the updated plot at 3 meter. Or if you want to do a 10 meter, it will just divide it divide that by 10. Okay. So after this is done, we can go back to our layout, and then we can right click and export near field data. And the reason why we want to do this is we want to import it to our 3D modeler to include the shielding. So I have the model ready set up. In this case, you can see I created I will show you the one with result actually. So in this case, you can see this is a Huygens box after you import it to the 3D modeler. And then you the excitation, mesh, analysis setup are automatically created when you import your model. So when we solve it here, again, we can plot the 1 meter result. You can go to the result, right click and create emission report, rectangular plot. And then here you can create like create emission reports for 1, 3, and 10 meters. So here at 1 meters, I will actually create a report at 3 meters, and then I will go back to and then I compare it with, let's see. Okay, so this is a 3 meter results. Let me delete this one. Yep, so now this is the 3 meter result we get from the 3D modeler tool. So so this one is the one. This is the 3 meter result we get from the 3D modeler tool, and then we can see it is matching with our result getting from the PCB layout tool at 3 meters. Okay, so the next step is we want to include the shielding. So we created a 3D enclosure. So in this case, I will show you how the enclosure looks like. We created this 3D component. This is the enclosure for our PCB, and then you can see the box is assigned as a perfect E. Perfect electric conductor in this case, and then we have some cutout at the front of the PCB. And then we will just add it we will place our PCB inside this enclosure. And again, we will use the same setup, but just analyze it again. In this case, now I will have the 3 meter result with the enclosure. And then I will go back and I will copy the data from no shielding, and then I will compare that with shielding. And then you can see that the radiated emission is much lower than before. And we can also look at the E field at a cup plane. In this case, I am selecting the XY cup plane, and then I'm plotting the E field. So this is the E field that you can see, and then you can see that most of the field are trapped inside this enclosure, and there are only fields escaping the shielding from the cutout. Yep. So at this point, here is the end of the demo. I'm just kind of quickly showing you what you can do combining the PCB layout tool with 3D modeling tool. Going back to one of the example, the lightning example Mark shows, that is you are treating the PCB as a victim, and then you have like some radiated field coming off the bus bar, right? So in this case, the PCB is a noise instead of victim. But yeah, you can play around that in the simulation. You can either treat your PCB as a noise source, or you can treat it as a victim, and you can do the analysis. Okay. Yep. So this is the end of the presentation.